All right, so today we are going to unlock the meaning behind the periodic table and make you an expert in being able to read this awesome thing right here. So first, atoms. Atoms are the base unit for every element on the periodic table. That's the smallest quantity you can possibly have of any given element. Atoms are made of 3 subatomic particles: your protons, your neutrons, your electrons. Protons, P positive, neutrons, and neutral. We use it with a superscript 0, and our electrons are negative. The protons and the neutrons are concentrated in the nucleus. That's where the majority of the mass of your atom is located. Your electrons are kind of whirling around the outside in these different energy levels or zones called orbitals. And the mass of your protons and your neutrons are both about 1, whereas your electrons in comparison are almost negligible. And think about the fact that a paperclip is a single gram, and the atomic mass unit, the unit in which we're measuring the size of protons and neutrons, is a 0 with 24 zeros after it, and then a 1. So remember, you have your tenths, your hundredths, your thousandths, and then 24 of those before you even get to 1. So this is an extraordinarily small value. They had to make up a new unit for it. So that's the atomic mass unit, and the electrons are even smaller than that. So just keep that in mind when you're thinking about the size of your atoms. So how to build an atom. We've done this with Play-Doh. We've done it on the computers, much to your dismay. We're going to do it again. So how to build an atom, you have to know how to read this periodic table. The first thing you have to be able to recognize is that this value right here, this bold blue number, usually it's the top, but really it can be anywhere. It's just the number without a decimal point. That atomic number is the number of protons. That is the defining characteristic of any element on the periodic table. If you change the atomic number, you have actually changed what atom you were working with, what element you were working with. If it doesn't repeat, there's only 146, 147, there's no doubles. All right, this is the defining characteristic. So the number of protons is your atomic number, and the other number on there that you'll see is your atomic mass, and that's the sum of your protons and your neutrons together. Again, we're not including the electrons in our atomic mass because they're negligible. They're so small. And how do we find the electrons, you ask? Well, I'm glad you asked. It's by the number of protons. We're assuming in this class that it's always a neutral atom unless told otherwise. So for this case, you're going to have the same number of electrons as you have number of protons. So let's pick an element here. Any element, we'll pick carbon. So carbon, C, has an atomic number of 6. So I'm going to draw my nucleus here. I'm going to say it's 6p+. And it's got an atomic mass of 12. So 12 minus 6 is 6. So I'm going to say I have 12 neutrons. And then I'm looking for, the next step is determine my orbitals. So I'm in the second period, 1, 2. So that I know I've got 2 orbitals going around here, which is going to contain all of my electrons. Now, where do I put those electrons? I know I've got a grand total of 6 electrons. 6 electrons total. But where are they going to be? That's the key. So that first orbital coincides with the first period. So on my first orbital, I'm going to look to my first period and see, oh, I got 1, 2 elements. They're both there because you have to fill in your first orbital before you can put any electrons on your second orbital. So that one's got to be full. So we put 1, 2. Now I'm on my second period, which corresponds to my second orbital here. I'm just going to count right across my periodic table. 1, 2, 3, 4. And that's how I know I've got 4 valence electrons. And that's what's going to determine your reactivity. So your valence electrons are those electrons that are located in the outermost shell, and this is going to be how you determine the reactivity of your element. So remember, how the periodic table is arranged is by your atomic number. It's not by your atomic mass. In the early days, it was by atomic mass, but we've since gotten smarter. We'll go ahead and look here at 52 and 53. You can see that the atomic mass goes from 127.6 to 126.9, thereby proving it does not increase by mass. Your periods are your rows. It's the periodic table. It increases as you go from left to right across the periods. Your groups are your columns. This is where you're arranged by your similar chemical properties, which is determined, of course, by your valence electrons. For like these guys right here, your noble gases, they are inert because they have those full valence shells, remember? But then we've got our halogens, super reactive because they've just got one more space that needs to be filled. All right, so you can divide your periodic table into three major groups. Those are your metals, nonmetals, and metalloids. We're going to start off with our metals. These are the vast majority of your periodic table. We have our imaginary stair-step line here. Everything to the left are your metals. Properties of your metals include they're shiny, they're luster, they're good conductors of heat and electricity, ductile wires, and they're malleable. They can be thin sheets. You can see they corrode easily. Here you can see my corroded silver from my grandma. And then you've got this malleable sheet of aluminum. So those are your metals. Your nonmetals are highlighted in red on your screen there. These are the ones to the right. These are divided by your metalloids. So your nonmetals are brittle, dull, poor conductors, heat, elasticity, can be solid, liquid, or gas. They're generally not malleable, low density. And remember your CHOMPS, the most awkward acronym of all time. These are your most common elements on the planet are your C, H, O, N, P, S. What are they all? They're all nonmetals. These tend to gain electrons easily, whereas your metals lose electrons easily. And then the wicked little stepchild here in the middle are your metalloids. So the cross between the metals and the nonmetals are solid, shiny, or dull, malleable. The thing that you need to know here are these semiconductors. They're important in computer chips. This is going to be your silicon right there, super important in computer chips. Metalloids divide your metals from your nonmetals on the periodic table. So then we're going to group our elements. This is where we're grouping them. Remember, again, that's vertical alignment is to do with the reactivity. So we're going to start all the way with the far left metals. These have one valence electron. Means they're super duper duper reactive. They want to kick that guy to the curb, so they're left with a full valence shell. Then these are the ones that explode in water. The reactivity is going to increase as you go down the table. And you can see that highlighted there. Lithium is a great example. Then we're going to move to our alkaline earth metals. That is the next group here. And remember, when we burn the magnesium, that's when the magnesium is reacting with oxygen. This is no coincidence because our magnesium here has two valence electrons. As you can see in that diagram pictured on the slide. So I want you to pause this, take a moment, and look at that chemical reaction of the magnesium and the oxygen. And recall what we did earlier today in class. All right, I'm so glad that you looked that up. Now you can see that the valence electrons are actually shared from the magnesium to the oxygen. Has to, needs to. They are great partners. Moving on. So our transition metals here, these are the big bulky ones in the middle. These are what you think of when you think of metals typically. So you've got your iron, your copper, your nickel, your zinc, gold, silver, and so on. And nonmetals, we're not really going to worry about their reactivity at this level, but just know those are your transition metals. Then we get over here to our halogens. This is like the key and the lock to our alkali metals. These alkali metals have an extra electron. These ones need just one. See, they're just one step away here from our full valence shells of our noble gases. Highly, highly reactive. We talked about how sodium and chlorine, we've used this example over and over, where the sodium has an extra electron, the chlorine needs one. Sodium explodes in water when it's raw. Chlorine gas will steal the water off your lungs, make hydrochloric acid. Not good for you, dangerous. Put them together, completely new chemical properties, table salt. And last but not least, our noble...
All students who read bus 196 need to be in the bus slot at this time. Ms. Franklin, please call the front office.
Yes, please do. All right, so now we're on to our noble gases. These ones, remember, do not need electrons or Bohr models for all of your noble gases. These are really fun because if you light them with electricity, they light up. And then down here at the bottom, we've got our rare earth. These are fun, they're important for technology and communication. They're not exactly rare. 95% of them are iron ore. And overall, your periodic table trends, you need to be able to pay attention to. I know this is a lot of arrows that you're looking at here. You need to be able to pay attention to the atomic radius. Knowing that as you go down, that atom is getting bigger and further out, moving further away from the nucleus. But the way, oops, sorry, my control for where you're looking is in my hand and I'm waving it all around. You're getting further away from the nucleus, so those electrons are getting further and further away. It makes them harder to hold on to, which makes that more highly reactive, especially over here. So francium is going to be a lot more reactive in water than, say, sodium or lithium as we move down the periodic table. You didn't follow me. Then it's going to get more metallic as you go this way as well. I'll move more slowly. So your periodic table gets more metallic as you go this way to this corner, which makes sense because these are your nonmetals. These are still metals. The electron affinity means the likely to hold its electron. These ones steal electrons. They are have a very strong electron affinity. These ones want to get rid of electrons. So they have a very, very weak electron affinity. So make sure you understand this table here as well. So remember, your key concepts is your periodic table is arranged by atomic number. Your atomic mass is the sum of your protons and your neutrons. So you can find your neutrons by taking your atomic mass minus your number of protons, and you get your neutrons. The elements in the same group have similar chemical properties, and the reason that is because they have the same number of valence electrons, which reactivity is determined by your atomic structure or the number of valence electrons. So, by the end of this week, and actually by today, you should be able to check your knowledge for any element on this periodic table. You should be able to find all the information here. And if you can't, then you need to come see me or you need to review this video. All right, guys, thank you so much, and happy studying.